Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture we were looking at the wave equation, and we saw how the wave equation is modified when we go from vacuum to any dielectric medium. And we also saw that the solution of a wave equation is a electromagnetic wave which has electric and magnetic fields perpendicular to each other, and both electric and magnetic fields are perpendicular to the direction of propagation. So in this lecture we will try to take a deeper look into how the electromagnetic waves behave. So to start with, let's look at the wave equation that we've already seen, right? So I mean, this is a general equation, three-dimensional equation, where Laplacian is dou x square by dou x square plus dou square by dou y square plus dou square by dou z square. But if I want to look at it's complicated to look at solutions in 3 dimensions. Okay, a general solution to a wave equation could be of this form. The electric and magnetic fields are given here. So we will understand this in a little bit detail later on. But initially, we are essentially expressing it as a real part of an exponential, right? And you have certain wave vectors, and there is a time dependence as well. So as I said, it's difficult to understand this easily in 3 dimensions. So let's consider the 1-dimensional case. So let me write the wave equation in 1 dimensions. So it will be d square dou square e by dou x square is n square by c square dou square e by dou t square, right? And what will be a solution to this equation? A simple solution could be of this form: e of xt is e naught exponential ikx minus I omega t. This is a simple solution. Okay, this is a solution we will consider here today. But there could also be another solution to this, which is minus of it. So e naught exponential minus of ikx minus I omega t. Okay, these are the 2 solutions that will be allowed. Okay, so one thing I want you to note is that the sign of the time dependence plays a crucial role. Okay, so in the first case we are considering the sign to be minus I omega t, the time dependence. Okay, in the second case it is plus I omega t, because minus and minus, right? It becomes plus I omega t, and that has some implications in the notation. So it turns out that the minus I omega t notation is used in the physics community, and the plus I omega t notation is used in the engineering community. So because of that, sometimes some parameters look different, but it's just the sign convention that they're adopting. Okay, all right. So we have this plane wave. Okay, so why do we actually call it a plane wave? The reason we call it a plane wave is that if you plot out the wave, we can easily see that it's a sinusoidal wave, right? But if you look at the constant phase fronts, okay, for example, I have this wave here which is moving in this sinusoidal fashion, and we know that the phase is, let's say, positive, we represent it by red, and the negative phase, negative part of it, we represent it by blue. So what's happening is the phase, the constant phase front is a plane. Okay, so so surfaces of constant phase are planes, and they are perpendicular to the direction of propagation, and they are direction of propagation. So because of that, we call this particular wave as a plane wave. Okay, I mean, it's easy to see that if because there's not even any y dependence. Let's say the propagation direction in this case is x. Okay, so there is in the perpendicular y and z direction, there is y direction, there is no variation, so it's a constant phase that way. All right, so this is a plane wave, and because of the Maxwell's equations, the way they are symmetric, if you calculate, let's say assume this exponential ikx dependence and then calculate the magnetic field, you'll also see that it's perpendicular. It will turn out, naturally it will turn out to be in the y direction, okay, the perpendicular direction, all right. And if you look at the way the energy propagates, it is going to be dependent on the cross product of the electric and the magnetic fields, and that is given by the Poynting vector S, okay. The time average of that is the speed with which energy propagates in a particular direction. So far, these are some things that you must have studied in the electromagnetics courses, right? So what I want to do is take one step forward, okay, and discuss what is known as a dispersion relation. It's a very important relation that helps us understand the way electromagnetic waves behave in a particular medium. So we are already familiar with the wave equation, right? We saw that, okay, the second order derivative in space is related to the time derivative. But in the past, in the previous lecture, we saw that this coefficient was mu epsilon. But why am I writing it as n square by c square? This is simple algebra, but I just want you to note this, you know. So mu is essentially relative permeability times mu naught. And similarly, epsilon is epsilon relative times epsilon naught. And so this will essentially turn out to be n square by c square, because we saw that mu naught epsilon naught is 1 by c square. And mu relative is 1. I mean, in this case, there is no magnetic response. And n is root of epsilon r. So because of that, this is how it's a different form of writing a wave equation. There's no big difference. Okay. Okay. So we have this wave equation. Let's consider the 1D solution that we mentioned in the previous slide. Let's say E of xt is equal to E naught exponential ikx minus I omega t. So I'm considering only one type of solution here, okay, minus I omega t. That's the sign convention I'll use in this course. So what happens? So let's apply this E. So if you take the LHS is now going to be second derivative in space dx square. So that is going to be minus k square, the same E, right? Minus k square E. Okay. The second derivative, if you take it, will turn out to be that. And similarly, RHS is going to be, if I just take the second derivative, right? Dou square E by dou t square, if I take, that's going to be minus omega square E, right? Of course, there's a constant term. So if I combine this, if I call it 1 and 2, if I combine 1 and 2, I'll end up getting k square equal to n square by c square omega square. Okay. So this is a very important relationship that tells us quite a bit. Okay. And that's why we give it a separate name. We call it dispersion relation. So if I rewrite in terms of omega, omega square is going to be c squared by n square times k square. What does this tell us? Okay, let's first consider the case of vacuum. Okay, if I take vacuum, if I take vacuum, my n is 1. So omega square equal to c square k square. So I can write out as omega square equal to c square k square. This implies omega equal to plus or minus ck. All right. So this tells us that the dispersion is linear for an electromagnetic wave. And I can plot it the way I have shown here. So if I have k in the x-axis and the omega in the y-axis, the relation is linear. The slope is essentially the speed of the wave, and both negative and positive case are allowed. So you have this sort of a cone. In 3 dimensions, it will be a cone. In 1 dimension, it's going to be the space between these two lines, omega equal to ck lines. All right. So now, what happens if you have a medium with n greater than 1? Okay. Let's say some medium with n greater than 1. Well, can n be less than 1? Do you know of any naturally occurring material that is having refractive index less than 1? I think the answer would be no for most of you. but it turns out that, yeah, you can engineer certain things, but of course you cannot modify it a lot. It depends on, we will study, when we study metamaterials, we can see how the n is going to change, all right? So if I have n greater than 1, what would that imply? So basically omega is now plus or minus c by n k. So if you have a medium which is having a higher index, then the slope is changing, okay? So that's why I'm depicting the, let's say, refractive index of 1.5 I have, I'm depicting with the blue line. So these are two media that are the dispersion relation changes, okay? So from the picture, if you look at this graph, you might be tempted to think that the frequency is a function of a wave vector. You change the wave vector k and the frequency changes. Is that something that makes sense? If you think about it, you'll see that the frequency is essentially a property of the source. So the way the electromagnetic wave is generated is dependent on the source. Just because that wave is incident on a piece of glass, the field varies at the source, that is going to be there, even in the medium. So it turns, even though it's kind of sometimes confusing, that you might think that the frequency is going to change, but the way to read this dispersion relation is that you consider a particular frequency, okay, and see what is a wave vector, okay. This is, let's say, omega naught, that is my source frequency. So if you have that wave vector frequency, what is the wave vector in medium 1? What is the wave vector in the medium 2? Okay. Typically when I say, if I consider n equal to 1, right, n equal to 1 air, I usually call it as k naught. Wave vector in that medium, I'll call it as free space wave vector or k naught. Okay. K naught, wave free space k, I'll say, okay. And any other medium, the k is going to change, okay. We will come back to it in a moment, but right now, yeah. So I want you to understand this. And also, you might be tempted to think that the dispersion is always linear, but it's not the case, okay. You can also have some modes in a structure which can cause the dispersion to be quadratic or parabolic, whatever. I mean, you can have a different shape, not linear, right? You can have higher orders. So this is one such example is a guided mode. You can have, let's say, in a waveguide, you can have modes which essentially have a flat dispersion here, or the mode is having the omega versus k relation relatively flat here. It has certain implications, okay. And in this context, I should also introduce two terms. One is the group velocity, one is the phase velocity. So when you think of the group velocity, that is essentially given by the first derivative of the omega versus k. So the d omega by dk is known as group velocity, and it essentially denotes how the speed of energy propagation, okay. Energy propagation velocity is a group velocity. Okay. And similarly, phase velocity is simply the ratio of omega by k and c by n, and this sort of, this is the speed with which the phase propagates. Phase propagation velocity, that's a phase velocity. Okay. In the case of simple dielectrics, right, like air, glass, and so on, the group and the phase velocities are same. But this need not be the case. There are some situations where you can have group velocity be much more smaller. All right. So why is this useful? Why is this concept of different case useful? All right. To understand that, let's examine this. Okay. Let's examine the electromagnetic wave, and we already saw that the dispersion is going to be given by this relation. The Ks are related to the refractive index. And in the previous lectures, we have seen that the refractive index is a number. If you take a particular wavelength, let's say 500 nanometers, I have a particular refractive index associated with that. If I take another wavelength, my refractive index will change. So it seems like the refractive index is real, right? This is the situations we have encountered so far. But it's not all situations. This is only for what we call as lossless materials, okay, or transparent materials. You can have refractive index to be only a real number. Whereas in absorbing materials, we will have n to be complex. All right. So I can represent n as a real part n prime plus I n double prime. Okay, so just as a caveat to people from different communities, in some textbooks they use this definition instead of plus, they use n prime minus I n double prime. So this is used when you use the I omega t notation. This definition is used when you use minus I omega t notation. So depending on the initial sign notation that you have taken, you have to choose. Okay, but in our course we'll simply use the plus sign all the time. So we are using exponential I omega t notation, minus I omega t notation. All right. Okay. So what is the implication of having a dispersion relation, of having the refractive index as complex? To see that, let's expand the k, wave vector k that we got, and we can write plus or minus omega c by c times n prime plus I n double prime. Okay, I mean this easily translates to plus or minus omega n prime by c plus I omega n double prime by c. Okay, the reason this is important is it can be seen by plugging it back into the original expression for the field. Okay, so we had E naught exponential ikx minus I omega t. This was the plane wave that we have considered. So now let me try to put the k that I have in the previous slide. Okay, so this becomes exponential I. Now my k is a complex quantity, omega n prime by c plus I omega n double prime by c. Okay, and then x minus I omega t. This is expansion. Okay, and if you further if you club the terms containing the imaginary part and the real part, you will see that I can write this as exponential I omega n prime by c. I will not do this. I'll just I omega n prime by c minus I omega t. This is one term, and then there's an I in the second term here. So there's an I here, there's an I here, so I can take a product of it. So if I separate out the exponential, there will be another exponential here, minus omega by c n double prime x. There should be an x here. All right. So what does this mean? So our solution, our plane wave, has two exponentials in it. One is the regular exponent x minus so ikx minus I omega t kind of an expression. The second part is a minus omega by c n double prime x. So what happens to the second term? Let's consider this particular thing. What happens to this term as x increases? As you go to larger and larger x, the ex or whatever the exponential term, right? Exponential this term reduces, right? It decays. So this essentially captures the decay of EM wave. And that is why we say that the imaginary part of the refractive index is it gives the absorption of the wave. Okay, this is absorption of wave. Okay, so that's why when you have the imaginary part to be 0, that means there is no absorption, and hence the material is transparent. Okay, so initially we saw that the transparent materials n is real. That is because the imaginary part is 0. That's why no absorption. Okay, but in general, the refractive index has to be complex. All right. And what about this other part? This is essentially what happens to this as x increases or x goes to infinity. What happens? Does it go to 0? No, it doesn't, right? It oscillates as x increases. Exponential, this term oscillates sinusoidally. So this we call as a propagating wave, propagating or traveling wave. It never goes to 0. It just keeps going on to infinity. Okay. Whereas this the exponential minus kx, or the decaying part, attenuates the wave. Okay. So how does the exponential look? How does the wave look like now? If I try to plot out the sinusoids, it's going to be, I can draw one as a function of x. If I plot out E of x, how does it look like? I mean, all of you must be familiar with this sort of a behavior, wherein you have a wave which decays. Okay. So this envelope is exponential minus omega by c n double prime x. All right. So this is the decay. So I want you to try out, let's say, this definition, right, of my electromagnetic wave, exponential ikx minus I omega t definition you take, and then consider what happens if n equal to n prime minus I and n double prime. Just consider what happens. Okay. So this is, we are considering the refractive index of a dielectric, right? This is the assumption we are making. This is the refractive index. Okay. The refractive index of dielectric. And if I substitute back into this exponential ikx minus I omega t, what will happen? How will the wave look like? And does that make physical sense? Okay. You are having a pure dielectric. Does that make sense? That's something that I want you to think about. And we will revisit this down the line. All right. So, just, summarizing whatever I have done in a better form than my handwriting. So you see the same things, absorbing materials are complex, have a complex refractive index, and then I can express my K as this one. Okay. I've written this part, but because of convention, the K corresponding to the K corresponding to the real part of n, we'll call it as beta. This is a propagation constant. This is usually referred as beta, which is a propagation constant. It's just a definition. Okay. Propagation constant. And the imaginary part, I'll call it as attenuation constant. So essentially I'm defining. So the same definition is given here. So you can just check this out. So the reason we are putting a 2 here is that the attenuation is defined as, the intensity that is absorbed over, intensity is always square of electric field. So that's why we put a divide by 2 here. Just attenuation constant is going to be some number again. Okay. So this is what this describes how the waves behave when you have, we saw that, the wave equation describes the waves, how they propagate in a medium. And we also saw that, okay, there is something called as a dispersion relation that is very, very important. And we saw some features of it, right? So this is what we have done so far. So I'll stop here for this lecture, and then I'll continue in the next lecture. Thank you so much.